Let's start talking about now, molecular formulas, molar mass, and basically using molecular formulas. So we already know, a couple things as far as we have, this notion of atomic molar mass. That if we look at, hydrogen, right, it has a molar mass of 1 gram per mole. If I have 1 gram of monoatomic hydrogen, right, I have 1 mole of hydrogen, or that monoatomic hydrogen, or 6.022 times 10 to the 23rd atoms of that hydrogen, right? So that's the notion of atomic molar mass. Now if we're getting to, molecular molar mass, and molecular molar mass is the sum of all the, individual atomic molar masses that basically make up the molecule or make up the formula. So as an example here, we could look at sodium carbonate. Right, there's our nomenclature again, CO3 carbonate, so -2 charge, and then we have those 2 sodiums that are +1. If we look at the molecule, we have, 2 times our sodium. Let's say our sodium is roughly 23 grams per mole. We have 46 grams per mole from the sodium in the molecule. We have 1 carbon at 12 grams per mole. So there's only 1 of those. And then we have 3 oxygens at 16 grams per mole, gives us a total of 48 grams per mole. So if we add that all up, we find that we have 106 grams per mole is, the molecular molar mass for the sodium carbonate. So what does that mean? It's kind of the same idea that if I have 106 grams of sodium carbonate, I have 1 mole of sodium bicarbonate molecules. I can even go further and say that I would have 2 moles of sodium, 1 mole of carbon, and 3 moles of oxygen based on that idea of the molecular formula, right? It's giving you that ratio of items together. Sometimes the molecules get more complex, but it's still the same, kind of process for molecular molar mass. So here we want to determine the molecular molar mass for, this iron nitrate molecule. This name would be ferric nitrate pentahydrate. I'm not too worried about the naming with this particular one. Well, let's just get the molar mass down as far as, you have one of each iron, so that's 55.8 grams per mole. And that's the atomic molar mass for the iron. If we look at our nitrogen, there's actually 3 of them. Each of 14 grams per mole gives us, 42 grams per mole. If we look at our oxygens, actually I have quite a bit. I have 14 oxygens. We have 3 from the NO3, but then there's 3 of those NO3s, so that's 9. And then we have 5 oxygens from the H2O hydrate portion of the molecule, so that's where the 14 comes from. So that's 224. And then lastly, we have our hydrogen. And we have 10 of them. Or a total contribution of 10 grams per mole. And if we add that all up, we find that we get a value, 331.8 grams per mole for this ferric nitrate pentahydrate. So that's, this idea of molecular molar mass. What can we do, with this idea of, molecular molar mass, and then in terms of, formula and etc. Let's look at percentage. In terms of percentage of elements within a molecule. And so when we get into percent of that element, we're really just looking at, the number of the element times its atomic molar mass, divided by the total, and that would really be the molecular molar mass times 100. So this is, a kind of a conversion feature for us. As an example, we could say, let's calculate the percent nitrogen in our molecule that we were just working with, the ferric nitrate pentahydrate. So if we're calculating the percent nitrogen, we're just now, looking at really the nitrogen contribution to the overall mass that we have, right? So, So for our molecule, that was 331.8 grams per mole, right? And that's from our previous example. As far as the nitrogen, content, well, there was 3 of them times our 14 grams per mole, or we have that total of 42 grams per mole. So this is the nitrogen contribution to the molecular molar mass. So my percent nitrogen would be equal to then my 42 grams per mole divided by my 331.8 grams per mole to give me a percentage of 12.6% nitrogen in this molecule. So that's how we can look at percentages in terms of an atom within a particular molecule. We could also look at it in terms of, substructure as well, in terms of, calculate the percent H2O. In that molecule, right? And so it would be kind of the same, gambit. It's just showing you that, we don't have to be in terms of a monoatomic or an element. We could be part of, a polyatomic in terms of the percentage. So we still have our 331.8 grams per mole. And now we're looking at our H2O content. And so we have 5 of them, each weighing 18 grams per mole. So we have a value of 90 grams per mole. So there's our H2O contribution. And so now our percent H2O can be determined, the same way. Dividing the contribution by the total, multiplying by 100, and we end up with 27.1% of H2O is in that ferric nitrate pentahydrate molecule. So that's really a conversion for us, right? It allows us to go between an element and then the molecule, or vice versa, or go from the element to maybe a polyatomic within the actual molecule. Let's look at using these types of chemical formulas. Or these ideas of molecular formulas. Started that with this idea of percentage, but we need to now, kind of utilize that within an actual calculation. So just realize that, the molecular formula is a mole representation. CO2, if I have, 1 mole of CO2, that means I have 1 mole of carbon. That also means I have 1 mole of oxygen, monoatomic oxygen. I apologize, 2 moles, right? Because we have CO2. So this molecular form is a mole representation, right? And really a conversion feature in our dimensional analysis. So that's the big deal that we have to understand, is that we have this mole representation, and that really this is a conversion feature for us in terms of how we can go from one thing to another in dimensional analysis. So we can, start simple maybe in an example, and say, well, how many, moles of hydroxide, are there in 10.5 moles of aluminum hydroxide. So here, kind of, we got to know our name, right? We got to know our nomenclature. It's kind of stemming back to the earlier part of this lecture with, hydroxide. What is that? Aluminum hydroxide. And so with our notion of hydroxide is a polyatomic. And we have aluminum hydroxide. And so aluminum, if we look at aluminum is in that 3A group. So it likes to be +3. So if we put those two together, that means we have, aluminum hydroxide, which looks like this. So there's our aluminum hydroxide, and basically we're just doing a simple mole-to-mole relationship. If we look at, where we want to kind of go here, right, we're trying to figure out, moles of hydroxide, right? And so that's the question mark. Right, and then what are we given? Well, we know that we have 10.5 moles of this aluminum hydroxide. So that's really where we're starting, is right there. So we have to figure out the conversion feature between the two, and that's really, the actual formula, right? The formula, as we're going, kind of states that, well, there are 3 moles of hydroxide for every 1 mole of aluminum hydroxide, and going further, right? And that's just that relationship of the formula, right, to the polyatomic. And now that allows us to keep going to then get at our answer, moles of hydroxide. So really just a simple conversion here, but trying to just have an understanding of, okay, how that molecular formula works in terms of the conversion. So we would want to start with that mole value, of the aluminum hydroxide. Set up our dimensional analysis. We want to get out of mole units for the molecule, the aluminum hydroxide, and we want to get into moles of that polyatomic, the OH minus. So there's our hydroxide, or I'm sorry, our aluminum hydroxide canceling out. And that gives us then our answer of 31.5 moles of hydroxide. So there's just, kind of the introductory type conversion as far as that is concerned. Let's, maybe take it an additional level, right? So here, we use the formula, but let's just, take it to something we'll see a lot more. Would be, how many grams of oxygen or, monoatomic oxygen are there in 12.5 grams of aluminum hydroxide. So more to the chase here as far as the question. And now we're looking at not going between a mole to mole conversion, really looking at kind of this mass to mass conversion. And the mass to mass conversion is an important one. So again, I like to break it down into where are we going and what do we know. So we're asked how many grams of monoatomic oxygen there are. So we're looking for a mass of O, right, or oxygen. And we're given this value, right, meaning that we know we have 12.5 grams of this aluminum hydroxide. And we can actually see there's our oxygen that we're looking for. So how much of that oxygen in this 12.5 grams of aluminum hydroxide is, O, essentially. So sometimes, in looking at these two disparate features, you might be like, well, what am I supposed to do? Where do I begin? And a lot of times I think of like a retro analysis, meaning, I kind of start from the ending. And I try to think of a conversion feature. And the most important thing that we have to really understand when we're getting into relating molecules and elements and all of that nature is that it's always a mole to mole game in relating elements to molecules, polyatomics, or vice versa. Moles is really the only, apples to apples comparison. Aluminum hydroxide has a different molar mass than oxygen does, right? They actually physically weigh different things. As far as 1 mole of oxygen weighs 16 grams, but that's not true for 1 mole of aluminum hydroxide, right? So we can't relate these two molecules on the mass basis, and that's true for everything across the board. The whole game is the mole game, right? Is the mole to mole game. You got to get them into moles. Once we're into moles, well, a mole is a constant number, right? It's 6.022 times 10 to the 23rd, just like a dozen is a constant number, which is 12. So that means I can relate 12 things of one to 12 things of another, right? It's an even keel or apples to apples relationship. And that's why we always have to get into moles of these things, because that is also that apples to apples relationship. So in that retro idea, I know I can go from moles of oxygen to mass of oxygen because I actually know the atomic molar mass of oxygen. And so now it's like, okay, well, how do I get at moles of oxygen from maybe this molecule? Well, now that's just looking at the formula, right? That's what we just, actually did, right? As far as that, well, there's 3 moles of oxygen for every 1 mole of the aluminum hydroxide. So that means all I really need to do is, okay, if I can get 2 moles of aluminum hydroxide, I can then get to moles of oxygen, right? And then I can get to mass of oxygen. So we have, like 3 different conversions here. Here's our first conversion. Here's our second conversion. And then here is our third conversion in terms of that. And the most important part is really, the second conversion, the mole to mole conduit. So if we start, right, we would have to calculate the molecular molar mass of the aluminum hydroxide. And so this is the first conversion. And it's allowing me to get out of mass of the aluminum hydroxide and get into moles of the aluminum hydroxide. I then can use my conversion feature which is the actual formula, to now go between moles and moles. So here is that second conversion, where now we're looking at taking out our moles of aluminum hydroxide and now converting it into an element that's part of that molecule. And then our third step would be to convert back to mass, but now in terms of the monoatomic oxygen. So there's our third conversion. And now we're getting out of moles of the oxygen, and we're now left into grams. And so that's our ability to go from mass of one thing to mass of another. And we end up with 7.69 grams of the atomic oxygen. And what's most important here that we can highlight is right here. Right, this is that mole to mole game, or mole to mole superhighway. Right, that allows for this relationship to happen on that apples to apples idea. So getting a little bit more difficult, right? We went from just moles to moles. Now we've gone from mass to mass, but we still had to use that mole to mole conversion. Let's take it up to the higher level. Okay, so let's take it up to an example now that incorporates that earlier idea that we talked about as far as, percentage of elements that's within a molecule. So how many grams of a, granular substance that is 92% of ferric sulfate hexahydrate so how many grams of that granular substance basically needs to be weighed out in order to obtain (20 grams of iron plus 3, or this idea of ferric ions at the end of the day? So there is our question. How many grams of this substance, which isn't pure, contains 92%, this substance contains 92% of what we want, which is the Fe2SO4 6H2O, or the ferric sulfate hexahydrate. And so how much of this substance do we need to weigh out in order to obtain what we want, which is 20 grams of iron? This happens a lot in chemistry, that what you're weighing out on the scale isn't necessarily pure, right? If it was 100%, well, then this would be a much easier calculation, but it just turns out that what we're weighing out isn't a pure substance. So that means we're actually going to have to weigh out more than what we would actually think in order to get, this certain amount of the molecule, or in this case, a certain amount of element that's part of the actual molecule. So again, I like to do that retro analysis, right? As far as, okay, we're looking for a substance, right? That's the question mark. Right, grams of the substance. And at the end of the day, this is what we want, the 20 grams, but that's really kind of the beginning portion, that we know we want 20 grams of iron plus 3. How do we relate, the actual two, right? And so this one's definitely a little bit trickier because, here we actually don't know molar mass. So the question would be so how do we relate? And the answer here would be in terms of this other percentage that we actually have, meaning that there is, this idea of 92%. We could write that a little bit differently in terms of saying that, well, we could say that, well, there's 92 grams of this molecule, right, for every 100 grams of substance, right? And so that's the relationship that we're talking about as far as how do we relate. Well, we relate using the 92%, right? So that's how we actually relate it to that. So I need to get in terms of somehow this mass of the molecule, right? And so now it becomes a connection between the earlier example, right? That means I know this now. So now that I get into the grams of the molecule, I know what to do, right? I got to get into, mass of that ferric sulfate hexahydrate. And I kind of don't have enough room here, so I'm just going to kind of do an L, meaning that now I can go to what I know from that prior example, that I can just now go to moles of the ferric sulfate. Once I get to moles of the ferric sulfate, I can then go to moles of the ferric ion, and then I can connect to where I began. So, apologize, running out of space there. So we have 4 conversions. We know we first need to go to moles of our iron plus 3. Then in the second conversion, we get into moles of the actual molecule. Our third conversion gets us into mass of the molecule. And then finally, our last conversion actually gets us to the answer, which is our grams of the substance. So we have 4 conversions within this process. And we just want to be really careful with writing out, everything with our dimensional analysis, because we're, going between elements or ions in this case and molecules. So, and then between molecules and then a substance. So it's really, advantageous not to just write grams or moles, but to really write, what we're describing in terms of the grams or the moles. So here we would convert using the molar mass for our iron plus 3. All right, get that off the periodic table. So there is our first conversion, allowing us to get to moles of the iron. Now we're at the second conversion, so we're getting into how that relates to the formula or the molecular formula. We have our iron plus 3, and then we have our molecule, the ferric sulfate hexahydrate. There's our second conversion. Here now getting out of moles of the monoatomic element, and getting into moles of the molecule. Let's fix that up just a little bit here, if I can. All right, because we should have, 1 mole out in front of that. And then we're off to the third conversion, which is now this mass, right? We got to get to molar mass. So we have, 507.6 grams per mole. I'm just, for space, right, realize that this is, for the ferric sulfate hexahydrate molar mass. So our moles of that ferric molecule are disappearing. And now I'm using the mass of that particular molecule to the substance. And so that's why we got to be particular. Right, we have 92 grams of this ferric sulfate hexahydrate per every 100 grams of the substance. So we're getting out of grams of our molecule here. Again, that's what we see in both cases as far as that molecule. And now we're left in grams of the substance, and that is our fourth conversion. And so that equals 98.8 grams of the substance right would basically contain 20 grams of iron plus 3 or ferric ions. So that's how we can, up the scale a little bit, now use percentages as well within this, molecular formulas and moles of molecules and moles of elements, moles of polyatomics. Can get a little bit tricky. Here, kind of showing everything in one step, if you will, from left to right. But realize you don't have to do that, right? Go stepwise if you want. Just do step 1, what's the answer? Then go on to step 2, step 3, etc., etc.